Yeah, we can be able to see. Please
Okay, thank you.
maximize it
Okay,
and
okay. So I will start my session today. Okay. As he gave in the introduction session, we are going to see about some concepts in your advanced data structure and its application. And today I'm going to cover two topics. One is your shortest path and one is your minimum spanning tree. Okay. So these two topics, they are there in your syllabus. It is in your 5th unit. Okay. And you're going to see these two topics. Okay. Okay, so already he gave an introduction about me, so I don't want to introduce myself again. Okay, okay. So before going inside the topics, you should know some basic things about your graphs. Okay, already you have been familiar with the basic data structures concepts. What is a graph? What is a weighted graph? And what is a non-weighted graph? Okay, we'll have a small introduction regarding these graphs, and then we will move on to the our topics, that is your shortest path and your minimum spanning tree. Okay, so what is a graph? Graph is nothing but it is a non-linear data structure. Okay, you can see the diagram here. This is a graph. Here you're going to have nodes as well as edges. Okay, so 0, 1, 2, 3, 4. Okay, so this rounded part, you call them to be a nodes, and the line or arc which is going to connect these nodes, you call them to be the edges. Okay, so totally in the above graph, you have 5 vertices, that is 0, 1, 2, 3, and 4, and you have a set of edges. That is from 0 to 1, you have an edge, again from 0 to 4, and 1 to 4, 1 to 3, and 3 to 2. Okay, so all these edges, they have been given in the set as E. Okay, so this is called as a graph. Okay, so you have a set of vertices as well as you have a set of edges. Okay, what is an edge? Edge is nothing but it's the line that is going to connect your vertices. Again, in graph, you have two types. One is called as a directed one and another one is called as an undirected one. Okay, so from the name itself, you can understand the thing, that is in directed graph, you have the arrow mark symbol, and in undirected graph, you don't have any direction. Okay, that is why in undirected graph, you call the nodes to be an unordered pairs. You don't have any order in the unordered pair. You can see the graph diagram below. Okay, so in undirected graph, you can take the pair as 3, 5 or 5, 3. You don't have any orders. Okay, again in the directed graph, you have an edge between each direction. That also you can see from the diagram. That is from 5 to 3, you have a direction, and from 3 to 1, you have a direction, and from 4 to 1 direction. Okay, so here it is automatically ordered. Okay, you have to take it as 4, 4, 1. You cannot take it as 1, 4 because the graph is directed from 4 to 1. Okay, so this is the difference between your directed graph and undirected graph. And then one more important thing here is weighted graph. Okay, without knowing weighted graph, you cannot see all these shortest path algorithms and minimum spanning tree algorithms. Okay, so what is a weighted graph? Okay, so in the first slide, I have told you what is a vertex, okay, and what is a edge. Okay, when we assign a weight to these edges, okay, that is called as a weighted graph. Okay, again, the graph what is shown in the slide, it is going to be a simple graph which is going to have a weighted edges. Okay, for example, G to A, you have the distance or the weight assigned as 10. Okay, so based on these distance only, we are going to find the shortest path or we are going to find the minimum spanning tree. Okay, so all those things what you're going to see further, they are completely dependent on these basics. Okay, so this is called as a self loop. What do you mean by self loop? Okay, if or whenever you see a graph, you have two edges, right? In this graph also, you have two edges. One is your A and another one is your B. Okay, so in case if you have the source vertex as well as your ending vertex to be the same. For example, here if I'm going to have the source vertex as A as well as the ending vertex also to be an A, you call them to be a self loop. Okay, a loop to itself. Okay, so in the above graph, you have the A as a self loop. Okay, so starting and ending edge, it is going to be the same. Okay, so this is a concept of your self loop. Okay, next we'll go inside the topic. Okay, so now we know what is a graph, what is a vertex, and what is an edge, and what is a weighted graph. Okay, so all those things we have seen here. Okay, next we move on to our topic, that is shortest path. Okay, so as I shared earlier, from the name itself, you can understand the main aim is to find the shortest path between the vertices of your given graph. Okay, so here the main aim is how you're going to find the path with the least cost. Okay, so whenever you're going to travel from one place to another, always you'll find the shortest route and the route which has the minimum cost. Okay, so similarly in the graph traversal also, we are going to find the shortest path between any two vertices in the graph. Okay, from the source to the destination. Okay, so you have so many paths existing in a graph. Okay, you can travel from the source to destination not in a single path. You can travel to so many paths. Okay, from among the paths, you're going to select the least one. Okay, so whatever algorithms or techniques we are learning in our subjects, okay, so where it is applied for, that is very, very important. Okay, so these shortest path algorithms, they are used in a variety of applications. For example, you are using in your Google Map, you are using in your road networks, okay, and you are using in your logistic research. Okay, and these algorithms, they are very, very useful for geoinformatics students because they'll be dealing entirely with their maps. Okay, so you're going to find the shortest route. Okay, next one, what are the classification available in these shortest path problems? Okay, totally you have 4 classification. The first one, it is called as a single pair shortest path algorithm or problem. The second one, it is called as the single source shortest path problem. Okay, third one is single destination shortest path problem. And the fourth one is all pair shortest path problem. So totally you have 4 classification. Okay, so among each classification you have a set of algorithms. Okay, we are going to see those algorithms in detail. The first one, it is called as the single pair shortest path problem. Okay, so the main aim is to find the shortest path between any given pair of vertices. Okay, so under this we are going to see an algorithm called A search algorithm. Okay, it is a very, very famous algorithm for solving this shortest path problem. Okay, so it is a popular technique which has been used in your games, in your web-based maps. Okay, and it is also called as the best first search algorithm. Okay, how it is going to work? Okay, that is very important. Okay, so first one, what you do is you maintain a tree of path from the starting node. Okay, so you start from the starting node, okay, and you extend those paths from the source to the destination like stepwise, okay, until you are going to reach the terminating condition. Okay, so you will very well understand this algorithm if I'm going to explain this with an example. Okay, so before that you should know the condition for this algorithm. Okay, how you are going to travel the graph. Okay, so here they have given the function of how you are going to calculate the cost of the path. Okay, so f of n is equal to g of n plus h of n. H is nothing but the heuristic function. Okay, so this heuristic function, it will be estimating the cheapest path from the current node to the goal node. Okay, and g of n, it will be calculating the cost from the starting node to any destination node. Okay, so you'll better understand when you see the example. Okay, so here you'll be maintaining 2 lists. Okay, so one is called as the open list and another one is called as the closed list. Okay, so in open list you will be having all the nodes that has been evaluated by the heuristic function. Okay, and in closed list you will be having all the nodes that have been visited, what you have visited and traveled. Okay, so these are the 2 lists you will be maintaining in this algorithm. Okay, so these are the steps involved in the algorithm. Okay, so in step 1, you open a list. Okay, so initially the open, it is going to have only your single node or your starting node. Okay, step 2, you have to check whether the list is empty. If the list is empty, you cannot proceed further and automatically you will exit your algorithm. And the third one, you have to choose the smallest value from this open list. Okay, and then I will be moving to the closed list. Okay, why you are moving to the closed list? Because closed list contains all the nodes that has been visited. Okay, so in case if this is going to be a goal state, okay, you return success, otherwise you exit it. Okay, again you have to extend this principle or expand to all other nodes, that is expand node n. Okay, to all the successive nodes. Okay, you have to travel from the source to the destination. Okay, so next you have to apply the evaluation function. Okay, you will see what is an evaluation function later. Okay, and finally you will be adding all the nodes in the list. Okay, so finally what happens when you travel all the nodes in the list, all the nodes will be added to the closed list. Okay, and finally you have to go back to step 2 and check whether the list is empty, to check any other node is still have not been visited. Okay, so this is the procedure what you follow this algorithm. Okay, so you better understand this algorithm with an example. Okay, see here you see the graph. Okay, you concentrate on the graph alone. You have so many nodes like A, B, D, C, E, G, J, etc. Okay, so the line which is going to connect, that is B to A. Okay, it is assigned with the value 6. Okay, so this 6, it is going to represent the weight as well as the distance. Okay, as well as the number 10 above A, it is going to represent your heuristic value. Okay, so the entire algorithm is going to travel upon these two values only. Okay, that is why we have seen that algorithm. We have seen that f of n plus g of n. Okay, so here you see the graph. Okay, so here we are going to travel from A to J. Okay, so I can travel from A to J in so many ways. Okay, I can go to F, H, I, J. Just see the graph alone, you can follow. And you can travel from A to F, G, I, J. You have so many paths available. Okay, so which is the ideal one? Which is the optimal one? Okay, so for that I have to calculate my heuristic function. Okay, so we have already seen the formula. Okay, so first from A, I can travel to B as well as F. Okay, so first I should calculate the distance for B. Okay, how will I calculate? What is the formula? Okay, so you see the formula. Okay, G of n plus H of n, right? Okay, so what is the G of n? H of n, H of n is 10. Okay, what is G of n? Is 6. So 6 plus 10, I'll get 16. Okay, so again from A, I can travel to F. Okay, so what is the heuristic function here? Okay, so here you see from A to B, if I'm going to travel, okay, I have to take the distance from A to B as 6, and I have to take the heuristic value of B, the destination node. Okay, so 6 plus 8, I'll be calculating as 14. Okay, again, I'll be traveling from A to F. Okay, what will be the distance here? That is 3 plus 6, that is going to be 9. Okay, so above F, you have the heuristic value. Just see the graph alone, you will follow. Okay, so above the F, you have the heuristic value 6. The distance from A is 3. So 6 plus 3 is going to be 9. Okay, this side from A to B, 6 plus 8 is going to be 14. Okay, so now you will be comparing 9 and 14. Which is lesser? Obviously, 9 is going to be lesser. So I will be traveling from A to F. Okay, so this is how you travel the entire graph. Okay. Okay, so from again, successively I have to apply for all these nodes. Okay, so from I have traveled from A to F. Okay, then I have to travel from F. Okay, from F I can go to G as well as H. So I have to calculate f of G and f of H. Okay, how will I calculate f of G? Okay, directly you have not reached G from A. You have reached G only through F. Okay, so how will you calculate? 3 plus 1. From A to F, it is 3. From F to G, it is 1. Okay, so 3 plus 1 plus the heuristic function of G. That is 5. That is 9. Okay, similarly, you have to calculate for f of H. That is from A to F and F to H. Okay, so which one is lesser? Obviously, f of G is 9. So you'll be traveling like A, F, and G. Okay, so similarly, you have to follow the same rules until you reach the destination node, that is J. Okay, so I have traveled from A to F, F to G. Okay, from G to from G, I can travel only to I. I cannot travel anywhere else. Okay, so that distance they have calculated here. Okay, again from I can travel either to E or to J. Okay, but my destination goal is going to be J, so obviously I'll be moving to J. So what is the ideal path or the minimum cost or the minimum weighted age with which I can travel from the source to the destination? That is A, F, G, I, J. Okay, so that I have highlighted here. Okay, so this is the ideal path in which you can travel from your source to the destination. Okay, so though there are so many paths available, you are going to choose the shortest path. Right? So this is called as the A* algorithm. So the next classification is single source shortest path problem. Okay, so here you will be choosing a given source vertex, okay, and you will be traveling the remaining vertices like the previous one. And here you have two algorithms. One is called as the Dijkstra's algorithm, and another one is called as the Bellman-Ford algorithm. And you are going to see in detail about the Dijkstra's algorithm. Okay, so before going to all these algorithms, that is your Dijkstra's algorithm, Kruskal or Prim's algorithm, all these algorithms are based upon this concept, what you see in your slide, that is called as the relaxation or updation concept. Okay, so the concept is very simple. You just see the graph. Okay, you after that you can follow the above points. In the graph you have three nodes, right? 0, 1, 2, and 3. From 1 to 2, the distance is going to be 2. From 2 to 3, the distance is going to be 4. Okay, so I'm going to label the node 2 as U and the node 3 as B. Okay, so first what you do, okay, initially you take the source to be 0 and all the other destination to be infinity. Okay, so this is the initialization here. Okay, the source node you take it as 0 and the destination you take it as infinity. Here what is the source node? That is 1. What is the destination node? That is going to be 3. Okay, so the destination 3 initially I'll be considering it as infinity. Okay, after upgradation it will change. Okay, so initially it is infinite. Okay, so what you do, you calculate the distance from 1 to 2, 2 to 3, that is 2 plus 4. What is 2 plus 4? That is going to be 6. Next, what you should do, whether 6 is less than infinity or not. Yes, definitely 6 is less than infinity. So you have to do the upgradation. What is the upgradation? What is 2 plus 4? 6. Okay, so I have to replace that infinity value by 6. So this is called as an relaxation or upgradation. Okay, that has been given as an if statement there. Okay, so what is the if statement then? D of u plus cost of u comma b should be less than your destination vertex. Okay, so what is the destination of u? You see from the diagram, it is 2. What is the cost from 2 to 3? It is 4. Is it less than infinity? Yes. So the condition is true. You go to the next statement. What is the next statement? I'm going to upgrade the distance of v. How will I upgrade? Distance of u plus cost of u comma v. What is the distance of u here? That is 2. What is the cost of u comma v? 4. So 2 plus 4, 6. So I'm going to replace this infinity by 6. Okay, so this concept it is called as an relaxation or updation. So you be clear with this concept because the entire algorithms, all the algorithms, whatever you're going to see, it is based upon this concept only. Okay. Okay, so first we'll see the concept of Dijkstra's algorithm, and then we can easily see if you can understand your algorithm as well as your Python implementation code. Okay. So this is the graph given for your Dijkstra's algorithm. Okay, so all in all these algorithms and graphs, our main aim is to find the shortest path. Okay, so here you're going to find the shortest path from the node, okay, to all the other nodes in the graph. Okay, to all the other nodes in the graph. Okay, so here we assume the weights. Okay, so weight of the edges, they are going to represent the distance between two nodes. Okay, for example, from 0, you see the diagram. Okay, from 0 to 1. Okay, what is the number assigned to that edge? It is 2. Okay, so this is a weight. Okay, so this weight, it is going to represent the distance between from 0 to 1. Okay, again from 0 to 2, what is the number given there? 6. Okay, so this is the distance between 0 to 2 as well as it is a weight from 0 to 2. Okay, so the entire algorithm is going to be based upon these weights as well as the number assigned to the edges. Okay, so as I said earlier, the relaxation updation rule, initially you will be taking the source node distance to be 0 and all other nodes you will be taking it as infinity. Okay, so that is what I have given as a right hand side like distance. You see, totally you have 6 nodes, that is 0, 1, 2, 3, 4, 5 and 6. Initial node you have taken as 0 and all other nodes you have taken as infinity. Okay, so our main aim is to travel from the source node to all other nodes in the graph. You have to travel all the nodes in the graph. Okay. Okay. So initially you have not visited any nodes. So I have taken the set of unvisited nodes here, that is 0, 1, 2, 3. You have not visited anything. Okay. So once you have visited, I'll be striking off that with that pink line. Okay. So you have visited node 0. So I have strike off that one. Okay. And next I have to decide in which direction I have to travel from node, whether I have to travel to 1 you see the graph, okay, from 0, whether I have to travel to 1 or I have to travel to 2. Okay, so that they have highlighted with their red edges. Either I should go to 1 or I should go to 2. Okay, so how will I decide? Okay, so again I have to calculate the distance. Okay, so what is the distance from 0 to 1? You see the graph, it is going to be 2. Okay, so initially the distance is going to be infinity. Now I have traveled from 0 to 1. So you see the right hand side, I have strike off that infinity symbol by 2. I have upgraded that. This process is called as relaxation or updation. Right? So 2 is less than infinity. So I'm going to replace that infinity by 2. Okay, similarly, I'm going to travel from 0 to 2. Okay, so distance is 6. So I replace that infinity symbol by 6. Okay, so now how many nodes I have visited? I have visited 0, 1, and 2. Okay, so whatever nodes I have visited, I will be adding that to the path. Right? Okay, next. So I have 0, 1, okay, and 0, 2. Which is the least one? 0 to 1. It is going to be 2. So I'll be selecting 0 to 1. Okay, again I'll be traveling from 1 to 3. Okay, so I can reach 3, okay, from 0, 1, 3, or I can reach from 0 to 3. Okay, so now again I have to do the upgradation, which is the ideal path. Can you follow? From 0 to 1, 0 to 2, you find 0 to 1 is better because it is 2. Okay, now I'm going to traveling to 3. Okay, so 3 I can travel either to 1 or I can travel either to 2. Okay, again I have to check the distance, which is the ideal path. Okay, so how will I do? 0, 1, 3, you see the graph, 5 plus 2, it is going to be 7. And 0 to 3, you check the distance, that is 8, 6 plus 8, it is going to be 14. So obviously 7 is going to be less than 14, so I am choosing that path. I have highlighted with that red line, right? So 0, 1, 3 is the ideal path here. Okay, so you see the right hand side, the distance 3 I have replaced by the infinity symbol has been replaced by 7. So all this is called as a relaxation or updation. Okay, so similarly, okay, from 3 I should go either to 4 or to 5. Okay, so I'll be calculating the same way the distance. So the distance is going to be 17 and 22. Okay, so as soon I visited those nodes, I'll be striking off that nodes. So totally I have visited 0, 1, 2, 3, 4. Totally I have visited some 5 nodes here. Okay, so 2 more nodes left. Okay, so for node 5, okay, so what is the option available here? Okay, so 0, 1, 3, 5, it has the distance of 22. Okay, so what is the second option? 0, 1, 3, 4, 5. Okay, so the distance is 23. So obviously you'll be choosing the 22. So this part 0, 1, 3, and 5. Okay, so next I have to travel, visit node 6. Okay, so what are the options available to reach node 6? Okay, so I'm calculating all the distance, all the possible ways, calculation here. That is from 0, 1, 3, 4, 6, what is the value, and 0, 1, 3, 5, and 0, 1, 3, 4, 5, and 0, 1, 3, 4, 6, all those combinations. Okay, so I'm going to calculate all the distances. Okay, so finally I find the path that is 0, 1, 3, 4, 6 to be the ideal one, because it is having a lesser distance when compared to the other one. Okay, so other distance it's going to be 22, 23, 25. Okay, so what this is the least one. So I'm going to choose this path. Okay, so now I have visited all the nodes and I have strike off all the visited nodes. Right, so I have replaced all the infinity with the distance what I have traveled. Okay, so this is called as the Dijkstra's algorithm. Okay, so the concept is very simple. Okay, so this has been all these concepts what you have seen now. Okay, they have given here in the form of an algorithm and they have implemented that in your Python code. Okay, so here what you will take in this algorithm, you will be taking a weighted graph. Okay, so condition is you should be having non-negative weights. The word non-negative is very important, because in all the examples what we have seen, we have taken only the positive weights. Okay, so the weights there should be always positive. Okay, and you'll be having a vertex, that is the source vertex, and the destination as V. Okay, so you are going to find what will be the output. It is the shortest path from your source to the destination. Okay, so what is the first step? Okay, as I told earlier, initial source vertex you consider 0, the distance of source to be 0, and the distance of the vertex, the destination vertex you consider as infinity. Okay. Next, you will be having a priority queue. What do you mean by priority queue? Okay, this you would have learned in your earlier chapters. Okay, that all those vertex which is having higher priority will be added in this queue. Okay. Next, you should check whether it is empty or not. Okay. In case if it is empty, you're going to choose the minimum value from this graph. That is by using the remove min function. This will return you the minimum value. Okay. Next, you should find all the minimum value will be stored as u. Okay. Next, you will be choosing all adjacent vertex from u. Okay, and then you should follow the relaxation or upgradation procedure. You have to replace that infinity value by using that condition. Okay, so that upgradation condition has been given here in the form of if statement. That is what we have seen in the previous slide. That is d of u plus the weight, it should be less than your destination. Okay, the previously we have seen in this slide, right? Like infinity, 2 plus 4 less than infinity. Is the condition true? Yes, I have to upgrade them. Okay, so 2 plus 4 is equal to 6. Okay, so same condition they have given here. Okay, then obviously you will change the value of the destination. Infinity you will replace by 6. Okay, then you will replace the label value. Next one is the Python implementation of your Dijkstra's algorithm. Okay, so here they have given a concept like adaptable heap priority queue. Okay, this you have learned in your earlier chapters. This is a queue where you will be storing the key value, where you will be storing the position. Okay, so all these things will be stored in this queue. Okay, so this course says initially you have to define your shortest path. Okay, hope you all know your Python code. You're going to define the function name. Okay, so inside you take the two arguments. One is your graph and another one is your source. Graph, whatever you take, it should be undirected as well as it can be directed also, but it must be weighted. It should have edges as well as weighted. And here you have a function called e.element. Okay, this is going to return the weight for your edges. Okay, and you initialize two empty dictionaries. One is called as D and another one is called as cloud. Okay, so D, it is going to have the distance of all your all the distance in your graph, that is from your source to the destination, and cloud, it is going to have a value of that distance. Okay, so next I'm going to call a function, the adaptable heap priority function, and I'm going to assign it to a variable called PQ. Okay, next by using the PQ locator, okay, this is nothing but it's again a empty dictionary, okay, where you will be finding the position of all these vertex and you will be adding them to the priority queue. Okay, so as you all know, the source, it is going to be, distance is going to be 0, and others it is going to have some infinite distance. Okay, so next I'll be traveling the vertices using your for graph. Okay, in case if your vertex is going to be the source vertex, you'll be assigning it as 0. Otherwise, you will be assigning it as infinity. Okay, next by using the peak locator, I'll be saving the location of all the vertex that I have visited. Okay, next you have to check whether it is empty or not. Okay, then only you can travel. In case if it is not empty, you have to find the minimum element and you will be adding to the dictionary, that is cloud. Okay, so once it has been visited or added to the cloud, it should be removed from the P locator. Okay, next you will find for other incident wedges where it will be located, that is opposite to U. Okay, so you can see from the graph. Okay, if for example, if you consider U comma V, V will be located just opposite to V, opposite to U, I'm sorry. Okay, so you'll be using the opposite function to find the opposite of U. And next you should check whether the vertex is there in the cloud or not, whether you have visited or not. In case if you have not visited, you have to find those weights, and this you have to apply the relaxation procedure. Okay, so that is what they have given here. That is d of u plus weight should be less than d of p. The same relaxation procedure, just the variable names have been changed. Okay, so 2 plus 4 less than infinity, no, sorry, yes. Okay, so you have to upgrade the distance. So 2 plus 4 is going to be 6. Okay, so each time you do this upgradation, and finally you will return cloud, which contains all the visited vertices. Okay, so this is called as the Dijkstra's algorithm. Okay, so the next one, it is called as the single destination shortest path problem. Okay, this problem also you will be reversing the direction of the edges in the graph. Okay, and you will be finding the shortest path. And again, here also you will be using Dijkstra's algorithm. Okay, so as we have seen earlier, I'll be moving to the next classification, that is called as all pair shortest path problem. Okay, so here again we are having two algorithms that is called as the Lloyd-Warshall algorithm and Johnson algorithm, famous algorithms in all-pass shortest path. And we are going to see in detail about Lloyd-Warshall algorithm. Okay, so here you're going to compute the shortest path between any two vertices, and it is an example for your dynamic programming approach. What do you mean by dynamic programming? Suppose if you have a complex problem, you will be dividing them to sub-problems and then you will be finding the optimal solution. Okay, that is what is called as a dynamic programming. Okay, so initially what you do in Lloyd's algorithm is first you'll be removing the self loop as well as the parallel edges. Okay, and next you will be initializing the matrix and you will be finding the distance between the matrix. Okay, so the self loop distance always it is 0. From A to A always it is 0. Okay, so if you see the graph here, okay, so all the diagonal elements it is assigned with a value as 0. Okay, so in case if I have a value from 1 to 2, okay, it has been given here as 8. If I have no direct connection between any two vertices, I'll be taking them as infinity, same as the previous one. Okay, so if I have a direct connection from 1 to 2, I'll be assigning them at 8. Okay, from 1 to 3, I don't have any direct connection. Okay, I'll be taking that value as infinity. Okay. So you better understand this algorithm by this diagram. Okay. So D0, D1, D2, D3, D4. Finally, D4 is going to give you the shortest path. Okay. So totally you have 4 rows and 4 columns. Okay. So how you have derived this matrix? You have derived this matrix from your graph. Okay. Well, so that is the distance from 1 to 1, it is going to be 0. And the distance from 1 to 2, it is 8. The distance from 1 to 3, it is infinity. So all these things you have derived from your graph. Okay. So what you do in this algorithm is from D1 I will derive D0 I will derive D1, from D1 I will derive D2, and it goes on. Okay, so initially I have the value as D0. Okay, from that I have to derive D1. Right. So D1 in the sense I have to omit the first row and the first column. Okay, that I have highlighted in the dotted lines there. You have to omit that, as well as you have to omit the diagonal elements also. That 0, 0, 0. All the diagonal elements I need not consider. Okay, so next one what you will consider, you see the top one. Okay, that is sorry, okay, this one, the top one. Okay, D1 of 3 comma 2. Okay, so you see the graph here. Okay, so D1 of 3 comma 2, you just concentrate on the matrix. Okay, so 3 comma 2. Okay, so D0 of 3 comma 2. What is the value here? Infinity. So I have to upgrade this infinity. What is the logic I am going to follow here? Okay, so I have taken as 1, D1. So I have to omit first row and first column. Okay, so what is the row and column value I have taken here? 3 comma 2 with respect to 1. Okay, so how can I split this? 3 comma 1 plus 1 comma 2, because with respect to the first row and first column. Okay, so 3 comma 1 plus 1 comma 2. I have to add 1 to 3 and 1 to 2. That's all. Okay, so now you see the value here from the initial matrix. What is the value for 3 comma 1? Okay, what is the value for 3 comma 1? It is going to be 4, right? What is the value for 1 comma 2? It's going to be 8. So what is 4 plus 8? It is 12. So I'll be replacing this infinity value by 12 in the D1. Okay, so the same procedure I have to follow for all the following matrices. Okay, so finally I'll be calculating the shortest path. Okay, so this is called as the Lloyd's algorithm. So next, so far we have seen about the shortest path algorithms. Okay, next we are going to see about the minimum spanning tree. Okay, so what is called as the minimum spanning tree? It is nothing but it's going to be the subset of all the edges in your graph. Okay, such that you visit all the edges but with minimum weight. So here you're going to have two algorithms. One is called as the Prim's algorithm and another one is called as the Kruskal's algorithm. Okay, so this is a greedy algorithm. What do you mean by greedy algorithm? For example, currently you'll be having a best solution, and next you'll be moving on to the another possible solution. Okay, from that solution you'll be moving to another best solution. So this is called as a grading algorithm. Okay, so in Prim's algorithm also the graph must be weighted, it should be connected as well as it should be undirected. Okay, so here randomly you will be choosing any vertex. Okay, you will be choosing any shortest any edge which is going to having a least weight, okay, and you will be connecting those edges, okay. So when you're connecting those edges, you just have to check whether it is going to form a cycle. In case if it is going to form a cycle, you reject those edges, okay. And finally, you will get a graph with all the vertices included in the minimum spanning tree. Okay, so you'll better understand by this diagram. You see this diagram. So you have initially you have a graph here, right? 6 to 1, 1 to 7, and you have all the weights assigned to it. Okay, so what is the minimum distance here from 6 to 1? It is 10. Okay, so from 6, next where can I travel? Okay, from 6 I can travel to 5, or from 1 I can travel to 2. Which is minimum? From 6 to 5 it is minimum, it is 25. So I'll be taking that part. So 6 to 5. Okay, again from 5 I can travel to 4 or to 7. Which one is least? 22 is least. So I will be traveling from 5 to 4. Okay, so similarly I have to travel the entire graph using this logic. Okay, and finally I will have all the nodes to be visited. Okay, you see the final graph. Okay, it is not going to form a cycle. Okay, so this logic, it is called as the Prim's algorithm. Okay, so this is an algorithm for your Prims. Okay, so input you will be taking an undirected weighted connected graph. Okay, with the n vertices and m edges. Okay, final output you have a minimum spanning tree. You choose any vertex to be the source. The destination of source, it is going to be the 0, and destination of V, destination of the final vertex or the destination is going to be infinity. Initially, the tree is going to be empty. Okay, next you will find all the keys associated with that vertex, all the edge weights associated with the vertex, and you have to check whether this priority queue is empty or not, and from that you have to find the minimum value. So in all the algorithms, the steps are going to be the same. Okay, you have to find the minimum value, and you have to add that minimum value to the tree, and you have to check the other edge, that is u comma v. Okay, and you have to follow the same upgradation procedure that has been given in the if condition, whether the weight is less than the final vertex. Okay, in case if it is less, upgrade that one. Okay, and finally add to the destination, and finally return the tree. Okay, so this is the Python implementation of your Prim's algorithm. Okay, so here I'm going to define the function as MST, and I'm going to take similarly, like the previous one, I'm going to take an empty dictionary. Okay, so it is nothing but the distance from any source vertex to another vertex. And again, I'm going to take an empty list, okay, called as tree. Okay, what is going to consist of all the edges in your tree. And previously we have seen the same thing, again they have repeated here. Okay, so that priority function I'm going to assign to the variable called pq. Again, the pq locator function, okay, from the vertex I'm going to add all the entries to the priority queue. The source it's going to be 0, and the distance, the final destination, it is going to be infinite. And next, using the for loop, I'll be traveling all the vertices. Next, I have to check the distance whether it's going to be 0. In case the node distance is going to be 0, it is going to be the first node. Okay, and I'll be taking this to be a root node. Okay, else it is going to be the infinite node. Okay, so whatever location I'm traveling, I'll be adding to the p locator. Okay, then finally you have to check whether that p is empty or not. In case if it is not empty, again I'm going to find the minimum element among these edges, and I'll be adding to the p to the queue, priority queue. Okay, so once everything has been added in the tree, okay, you have to delete all those edges from the p locator, because you have located the edges, you have located the points position. Okay, so you have to delete all those nodes from the p locator. Okay, so finally you have to update the tree with all these edges you have visited. Okay, so this is called as the Python code of your Prim's algorithm. Okay, so next, using the for loop, okay, I have to find the opposite edges. Okay, and previously we have seen this function, that is link dot element. It is going to find the weight of your edges, and again you have to check whether your weight is less than the distance. Okay, and you have to follow the upgradation principle and add it to your entry. Okay, and finally return the tree with all the edges visited, provided it doesn't form a cycle. The next one is called as the Kruskal's algorithm. Okay, here also I'll be sorting the edges from the low weight to high weight. Okay, so here I'll be traveling all the vertices in the graph. Okay, here also it should not form a cycle. Okay, so you visit all the edges. Okay, So initially what you do here is first you draw the vertices of the graph separately in a paper and then you connect these edges. Okay. So you better understand by seeing this diagram. Okay. So here you have a graph. Okay. So totally how many nodes? 7 nodes. So initially I have drawn the nodes alone separately. Next I have to check which is going to have the minimum one. That is from 1 to 6 it is 10. What is the next minimum? From 4 to 3 it is 12. What is the next minimum? 7 to 2 it is 4. Similarly, I have to connect all these things and then I have to get the final one. Okay, so this is called as the Kruskal's algorithm. Okay, so similarly here, what will be the input? The input is going to be your connected graph with your vertices and edges. Okay, so what will be the output? The minimum spanning tree. Okay, you have to take the individual vertex. First, you have an initial cluster that is 0, 1, 2, 3, what you have drawn separately. Okay, so this is one cluster. Okay, next you have a priority queue. Okay, which is going to have all the edges. Initially the trees are going to be empty. You have to check whether the tree has n minus 1 edges, and from that you have to find the minimum element. Okay, and from that you have to find the cluster, initial cluster and the next cluster. Okay, so in case if for both the cluster it is going to have some common elements, for example 1 to 2 or 2 to 3, you're going to have a common element as 2. Okay, so in that case you add that edge, that is u comma v to t, and you merge them to be a single cluster. Okay, so this is called as the Kruskal algorithm. So the next one is a Python implementation of this Kruskal algorithm. Okay, so here also you create an empty list which is going to have all your edges. Okay, and next you have your heap priority queue. Here also you're going to have key value pairs for your entry. Okay, and that has been assigned to the variable called PQ. And here you'll be using a function called partition, because why you use partition? Because I'm going to take the individual nodes from the graph, so I have to partition it. Okay, so I'll be assigning that to a variable called forest. Okay, again I'm going to take one more empty dictionary, and then using the for loop I'm going to visit all these vertices. Okay, and all the individual vertices I have to combine by using the make group function. Okay, and again using one more for loop I have to travel all the edges, and using e dot element I have to find the weight of these elements. And finally next I have to find the size of the graph using the vertex count function, and check whether the length of the tree is less than size minus 1, that is n minus 1, and you have to check whether it is empty or not. In case if it is not empty, you still have some nodes to be processed, and from that I have to find the minimum element, and I have to find the endpoint function from where it starts and where it ends. Okay, and you have two variables here, that is a and b. They are nothing but the position of u comma b. Okay, source and the destination vertex, and I have to check whether they are equal or not. If they are not equal, then it means it is an edge from a to b, and I have to add it to the tree. Okay, by making use of some union function. Okay, so this is called as the this is what we have seen is the Python implementation of your Kruskal. And the next point is disjoint point, partition, and union find structures. Okay, so this concept you should see before seeing the Kruskal algorithm, because mainly we are going to use this concept for your Kruskals only. Because in Kruskals we are going to divide this graph into so many partitions, and finally you are going to join or merge those partitions, right? So that is the concept here. Okay, so this concept, it is going to manage your partition of elements. That is here, it is going to help to manage your disjoint sets. Okay, so it is the main motivation for your Kruskal's algorithm. Okay, so how you are going to merge your neighboring trees. Okay, so here you have a universal of elements. Okay, that has been organized into disjoint set. You will call these clusters. That is, we have seen in the graph, right? 1 to 2, 2 to 4. All these clusters you call them group. Okay, for a group you have a designated entry. You call them to be a leader. Okay, so totally you have three methods here. One is called as the make group, another one is called as the union, and another one is called as a find p. Make group, you're going to make some groups whenever a new element is added to it. Union, I'm going to merge any two elements or groups knowing their position. Okay, what is the find one? It is going to return the position of the leader of the group. Okay, so these are the methods here. Okay, so here again you have two implementation. One is called as an sequence implementation. The concept is very simple. I can divide all the elements into some sequence such that the first position it is going to be some leader. Okay. Again, I am going to use the union operation. I can join all these sequence into one cluster. Okay, so you see the diagram here. Here you have three sequences, A, B, and C. Okay, so A is one sequence, B is one sequence, and C is another sequence. So the elements are ordered in their increasing order here. Okay, for example, for A, 1 will be the leader, for B, 2 will be the leader, and for C, 5 will be the leader. Okay, so this is called a sequence implementation of these partition implementation. Okay, the next one is called as a tree-based implementation. Here also the concept is very, very simple because you're going to combine two trees. Okay, so here you have two trees, that is FDG and CHEB. Okay, so I'm going to combine these trees by taking the F to be the common root. Okay, so this is called as tree-based partition implementation. Okay, so how will you do this implementation? By using by union by size. Okay, so you'll be finding the position, you'll be finding the number of loads, elements in that graph. Okay, always you make the smaller group to be the child of a larger group. Okay, so that is called as union by size. Okay, so next one it is called as a path compression. Okay, so path compression, what you do, you will reset the parent. Okay, in case if you're having a higher value parent, you will reset that node to be the root node. That is called as path compression. Okay, so this is the coding for this partition. Okay, so initially you will be using the union find structure for maintaining all these disjoint sets. Okay, so you'll be finding the position, you'll be allocating the slots. Okay, next you will be creating a new position for the leader. Okay, and you'll be finding that element name, size. Okay, what are its parent. Okay, and next you will be finding returning the position of these elements. Okay, so all these things will be done in this partition class. Okay, next after doing the selecting the element, making the position, finally what you do, you make some groups, you join everything, right? So that has been done by the make group function. Okay, so the new group, what are the elements it contains and what are the position it's going to return. Okay, for example, if you're going to have a leader in the group, what is its position? In case if that element is not going to be the leader, what is the next leader? Okay, so all these things will be done here. Okay, so finally I'm going to merge all these elements P and Q. Okay, so finding its position has been done here. Okay, that is A is equal to self dot find, B is equal to self dot find. Okay, and you have to check whether A is not in B. Okay, in case if A is not in B, either A should be A will be greater than B or less than B. Okay, in case if A is going to be greater than B, okay, you will assign the parent as A. Otherwise, the parent will be B. Okay, so that's all for today's session. Okay, hope you all understood. And thank you for your patience for listening to my session.
Yeah, Sumathi, it was a neatly and tightly packed session like this.
So because you have told me, right, the students have to go to the next session.
Yes. But perfect delivery. What I feel is, apart from the textbook content and reference content, you have given us such a neat and the way of understanding the topics will be easier when you are delivering. Okay. And also, I was attending for the past 15 minutes, and it was a very perfect and neat delivery.
I'll be happy if the students understand the concept. That's
yes.
Okay.
Thanks for sparing your time and let us. Is anybody having any coding? Students?
Students, I have shared this PPT with your professor. Okay, if you want, you can get it from them. And if you have any doubts, you can ask me anytime. Okay, I will help you. Okay. So my all the best wishes for your examinations. Okay, prepare well for your examination. Go through all the concepts. Okay, and my advice is you learn from the textbooks. Okay, don't follow any local author books.
Yes, that is the great thing. We used to, myself and our HOD often say this content. Please refer text. Don't go for any local author books.
Yes. The day before the examination, if you refer some local author books and you write something and go. Okay, so that will not help you. Okay.
Definitely.
And one more thing, you become expertise in any one field, whatever field you like in your subject. Not all the things you cannot become an expert. You choose a one and then you become an expert, either C, C++, whatever it may be.
Definitely.
Okay. Thank you, students. Thank you.
Thank you. And thank you. One more thing I failed to say, Sumathi is my schoolmate and in a long travel. So thanks for providing the opportunity and sparing your 1 hour time with us and bringing our students the nice package for today. Data structure, as this is the future industry-based subject. we need the strong foundation. I guess today they might have gathered some useful information as far with the subject and also for your delivery. Thanks for sparing your time, and thanks to our HOD for providing this option. And thanks to all the students for politely listening and taking notes throughout the session. Thank you. Thank you very much.
Thank you. I'm so happy they have taken notes. Happy to hear.
Thank you.
Okay. Thank you, sir. Kalipan, sir. Thank you. Thank you so much, sir. Sir.
Thank you, madam. Thank you.
Thank you. Thank you, sir. Thank you. Thank you, women.
Thank you. Thank you.
Thank you.
Bye.